All right, so yeah, last time we derived the Maxwell-Boltzmann distribution. Let's just remind ourselves of what that looked like exactly. So, looked something like this. So this is dv, the distribution function. This is v, the speed. For a given temperature, it looked something like this, and I'm probably going to screw it up horribly. So it like parabolically increases for a little bit of time, and then it exponentially dies off. So something like that. Okay. So basically in this region right here, you can call that like parabolic domination. In this region over here, you can call that exponential decay. Okay. So we have basically three different velocities that are kind of important to us that we can calculate pretty readily. Obviously, there's one unique velocity right here, which corresponds to the maximum of the distribution. So that we'll just call V max. And how would we calculate that? Well, anybody? What would you do? You would just take dv d of v, set that to 0, right? And so since this thing, it doesn't flip concavity in any point in time, you're guaranteed that all of these are going to be maximums instead of minimums. So, I mean, technically, whenever you take the derivative and set to 0, you're just extremizing some function. But this is the maximum. So when that's satisfied, you can define V max. Okay, so that's one thing we can do. What else do we have? We also talked about the root mean square velocity. We calculated that last time, or at least reminded ourselves of what it is. And that ends up being 3kt over m. I guess I should also write over here that V max. Oh, what's that? It is square root of 2 kt over m. One other thing we could calculate is what? The average speed, right? How would we do that? How do we calculate averages? Anyone? So we could take v, multiply it. Yeah, integrals. Integrals are always going to be your friend. Yeah, so basically if you're taking the average with respect to some distribution, so before we were talking about just like Boltzmann factors, in that case, like the Boltzmann factor was effectively your distribution. Now we're talking about specific distribution, the Maxwell-Boltzmann distribution. So if you're looking at the average for that distribution, you just take your variable, you integrate it against that distribution. And if we carried out that integral, which I won't do explicitly because we've done stuff like this over and over, we would get 8 kt all over pi times m. And so mixing up these three speeds right here is a very, very, very common mistake for all kinds of people that I've talked to whenever they take labs where you have to do data analysis of some type. So Vmax corresponds to this one right here. VRMS, this might be a little bit exaggerated, so don't take this to be quantitatively correct, but it's qualitatively right. VRMS lies somewhere over here. And if we were to write it out, V bar is somewhere over here. So basically, V bar always is going to lie in between Vmax and VRMS, and then VRMS and Vmax are the outer bounds here. So just making sure that we all understand the distinction between what these three different speeds are. That can be a common tripping up point. All right, so now let's do some little calculations. Let's consider, for example, nitrogen at room temperature and pressure. So consider N2 at room temp and pressure. Okay, so if you look this up and you calculate the mass for an N2 molecule, it is like 4.65 times 10 to the minus 26 kilograms. So if we put in this mass and then the temperature that we need into the max at room temperature, N2 will have the maximum speed of 422 meters per second. And so I'm just using the expression that I wrote down here. So it depends on the mass of whatever you're talking about. So basically, if it's bigger, it's going to be moving slower on average, which makes sense. And if the temperature is greater, then it's going to be moving faster on average. So if you put in room temp, about 300 Kelvin, and the mass of nitrogen in there, you get 422 meters per second. Okay, so that's all well and good. But let's say we don't want to find a specific, speed. We want to find like what the probability is of a molecule being like at some speed or greater than it, or like in some range or something like that. That's a more useful question to ask. So let's ask the following question. So what is the probability of V being greater than, for example, 1,000 meters per second? So obviously these are going to be huge outliers in terms of the speeds, but they're definitely allowable because you have the highest probability being the V max right here, and then you have this whole exponential decay of speed. So I mean, it goes all the way out to infinity, but obviously it's exponentially decaying. So let's ask, what is that? Well, we want to calculate the probability of V greater than 1,000 meters per second. What would we do? Anybody? What do we want to do with this distribution? I think Luke already had it. Integrals, integrate. Yeah, Jerry's got it. So yeah, we just want, this distribution is a probability distribution. So if we just take that point, integrate it all the way out to infinity, that'll tell us the probability of being greater than that speed. So if we take our Maxwell-Boltzmann distribution, we can pop out all of the constants that appear in it. So the constants that appear in it are these. No, there's not an M there. K times T to the 3/2. And the important part is that we want to integrate from 1,000 meters per second out all the way to infinity. And the distribution looks like this. All right. So now that we're considering these definite bounds right here, this thing can't be integrated analytically. We can't get a nice clean expression in terms of basic functions on the right-hand side. So you have to take this and you have to throw it into a numerical integrator. So I'd recommend, obviously, Python or Mathematica or MATLAB or whatever your favorite language is. But if you do eventually evaluate this for all of the relevant variables, then you get 0.0105. So if we move the decimal over 2, we get the percentage. So we have about 1% of the total population. It's the probability of finding at any specific speed, 0. Yeah, I guess if you treat this very, very literally, and you just count up like an infinitesimal, you count up a specific spot, then yeah, I mean, it's technically 0. But we're always going to be counting like a little bit of a range in here somewhere. And so think about it in terms of what's most likely relative to what's less likely. And the best way to do that is just think in terms of this distribution itself. But yeah, that's an interesting question, Safe. So we found that there are 1% of the total population. They're going to be V greater than 1,000 meters per second. D of V has a defined value. Yes, it does. Okay, so that's all we've got for now on the Maxwell-Boltzmann distribution. So Now let's talk about the relationship between partition functions and free energy. Okay, so previously in like the earlier sections, when systems were isolated and they had some fixed energy, in that case, the multiplicity function was basically the most important thing that we wanted to calculate, right? Because with that, then we could calculate the entropy, and then we could use all of our thermodynamic relations to calculate anything else we wanted to know. So like that was the fundamental quantity almost, was the multiplicity function. So likewise, now if we're talking about systems that are in equilibrium with a reservoir at some defined temperature T, the analogous quantity to the multiplicity now, what we've just found is that the analogous quantity is the partition function. So if we know the partition function z, we can basically calculate everything that we want to know. So we might ask, is there some kind of second law type relationship for z, the partition function, like there is for s? So I'll just write that out. So is there a second law, I'll call it a representation for z? So that's the basic question we want to ask ourselves. And so has anybody read ahead? Does anybody have any thoughts about what this will be? So whenever we're in contact with a reservoir, right, what's the analogous quantity to the entropy? So if we can get you're close safe. So when we're in contact with a reservoir, we can get heat for free, right? So what's the relevant state variable in that case? Yeah, okay, I think George is on the right track. So yeah, in that case, you can get heat for free in the form of minus Ts, right? So then the relevant state variable is the Helmholtz free energy, right? It's F equals U minus Ts. So that's what you might guess. There might be some relationship between Z and F, is I guess what I would have thought if I didn't know this. So let's recall the Helmholtz free energy, which we actually just used for the homework problem, one of the homework problems we do. So recall that F is defined as the average energy minus T times S. And we have this relationship. We have that del F, del T, with V and N held constant, was equal to minus S, okay? So you could quickly remember this if you go back and remember your thermodynamic relations for F and the other variables. Okay, so what could we do here? Well, we could solve for S. So yeah, Saif, what's your question? Yeah, so actually everything we've been talking about in chapter 6 so far has been systems in contact with a reservoir. So that's actually how we derived like the Boltzmann distribution and the Maxwell-Boltzmann distribution. So the T that you always see appearing in all of these equations is the temperature of the reservoir that the system is in contact with. Yep. And so that's why this is a relevant question to be asking right now, because the Z that yeah, that's like the main thing, is that this Z is specifically the canonical partition function. And so we haven't really said the other partition functions, but the canonical partition function is the one where you're in contact with a reservoir of temperature T. But there are other types of partition functions as well. So, okay, let's solve for S. Okay, so if we do that, we solve for S in here, for example. We can get that, what, F minus U all over T. So just subtracting the U over that side and then dividing by a T. that will be equal to minus s. Okay, so at that point we could equate this expression, the one that I just solved for s, to this expression right here. So take them, put them together, and what do you get? You would get that del f, del t, v and n held constant is equal to f minus u all over t. Okay. Now, hopefully you've got that down. I'm going to flip the page. Okay, so now we're going to consider quantity, which we won't give a name to just yet, but we'll consider the quantity minus kt ln of z. So this looks analogous to our expressions for entropy, but now z is playing the role of the multiplicity. So let's just look at this. So let's take derivative with respect to temperature of this expression right here. So it's fairly straightforward. So there's a temperature dependence here, just sitting outside. So there'll be minus k ln of z. And there's also a temperature dependence hiding in this z factor, right? So the partition function depends on what temperature you're talking about. So we have to actually take that into account. So in z, we've typically been writing the temperature dependence as being absorbed into this quantity beta, which we have defined as 1 over kt. So we can just use the chain rule to find the derivative in terms of that. So we can take del beta, del t, times del over del beta on ln of z. Oh, sorry. Yeah, there should be a log there, shouldn't there? Yeah. So just changing derivative with respect to t into a derivative with respect to beta. So you can do that just by using the chain rule like that. Okay, so now if we do that, we can take the derivative with respect to beta. We could have done it with respect to t as well, but this is just the conventional way of doing it. So we would get the following: 1 over kt squared, 1 over z, the partition function, del z, del beta. That is equal to u all over kt squared. And so I'm just using the fact that we showed, at least for the homework question, that minus 1 over z del beta is u. Okay? So that's all we got going on there. Now let's just take this, plug it back in up there. And what do we get? So we have minus k ln of z minus kt all over kt squared times u. So this t cancels out, that k cancels out. And we just have minus k ln of z minus u all over t. Okay. So if we look at this expression right here, and we look at our previous expression, where is that? So this expression right here, we can line up some quantities. We can make some educated guesses now. So we said that we could write, when we take the derivative with respect to the temperature of F, the Helmholtz free energy, we hold V and N constant, that it gives F over T minus U over T, right? So now we're saying if we have this other quantity, we're going to call it minus KT ln of Z, didn't name it yet, and we take the derivative with respect to the temperature, and we can also implicitly hold V and N constant since nothing depends on them here, that we get minus K ln of Z minus U over T. So the U over T matches up nicely between these two expressions. So we might guess that F over T is this quantity right here, the minus K ln of Z. So let's go ahead and call this quantity F tilde. It's minus KT ln of Z. And if we make that substitution up here, we see that it obeys the same relationship as F. Specifically, the same differential relationship. Does everybody follow that? So we're basically just lining up this expression, that derivative, with this expression right here. And so now we just need to show that F tilde and F are actually the same thing. So we've got a differential relationship that says that they're the same. But in order to show that they're actually the same, you need to prove it for at least one initial condition. Because if they don't agree on their initial conditions, then they don't agree overall. So for example, let's take the easiest thing. So take t equals 0. In that case, we have that f is equal to just u minus 0, because the ts term just goes away. So that's just u. And if we're talking about the system in contact with a reservoir, then this is going to be our minimum, our lowest energy state, because when the temperature of the reservoir is 0, our Boltzmann factors, right, they tell us that all of the other higher energy states are infinitely suppressed. So the only accessible energy at t equals 0 is going to be u naught, or the ground state. Okay, so that's that for f. Now if we want to evaluate f tilde at the same place, it's going to be basically the same reasoning. So take f tilde, it's defined as minus kt ln of z. And let's evaluate that at t equals 0. So this z right here, remember, basically looks like a sum over E S times beta, right? And beta is just 1 over KT. So again, if we set T to 0, this sum is only going to pick up the lowest energy state, because all the other ones are infinitely suppressed. So it'll only pick up whatever the lowest E value is. So again, this is just going to be the ground state, U naught. And thus we've shown very trivially that F tilde and F are actually the same thing. So we can say outright now that F, the Helmholtz free energy, has a similar relationship to the entropy, but now the partition function plays the role of the multiplicity. So this is our new kind of a way of thinking about the second law in terms of the partition function. So the partition function kind of plays the same role as the multiplicity. And so then using this, you could calculate all kinds of thermodynamic identities, just like you do for F previously in previous chapters. And so then as long as you know whatever the partition function is, you can calculate all of those thermodynamic identities straightforwardly. So the partition function is very, very powerful in this situation. As soon as you know it, you know how to calculate everything effectively. So finding the partition function is always your main goal when we're doing systems in contact with constant temperature reservoirs. Yeah. Mm-hmm. Yep. Okay. Yeah, so maybe this wasn't super clear. Here, let me clear this up a little bit. So maybe I can fit it in here. Okay, so on the previous slide, we had del f del t with v and n held constant is equal to minus s, right? And using that, we showed that it equals f minus u over t. So f minus u over t. So we know that f obeys that relationship, right? So now all I was saying was basically let's consider this other quantity. Let's take the same derivative, and then we can compare the two. So basically what we showed here is that if you define this other quantity f tilde, and you take the derivative with respect to the temperature, and again, you hold v and n constant, that you get minus k ln of z minus u over t. And so since this is a differential relationship, you can't necessarily just equate f tilde to f right away. So we can't necessarily just say that f is minus kt ln of z. So all we were doing here was we were saying, okay, well, we've got this differential relationship. It looks like they're the same thing. Let's consider one specific position here and show that they actually are the same. So if you've got a differential relationship between two things like this, you just need to show that they agree with each other at least one spot. Does that help at all? Okay, cool. Yeah, not a problem. All right, we don't have too much more to go. Gotta finish this. All right, so next section's pretty quick. So we just want to detail exactly how we can deal with partition functions for composite systems. So basically where you've got a system composed of two parts. All right, so let's just suppose that we've got a system that can be broken up into two separate systems that don't have any kind of interactions. They play nice with each other. Well, then the total partition function for the system, that is always just going to be e to the beta e of s. But in this case, we're supposing it's broken up into two. So we just break up e of s into respective energies of system 1 plus the energy of system 2. Since there are no interactions, you can do this. Okay? So, also, if the particles in these systems, you don't even have to say particles, just the different states of the system. I'll just say particles because that's usually what we're talking about. If the particles of the systems are distinguishable, then we can do the following. We can take z total, and we can break it up into the sum over 1, sum over 2, e to the minus beta e of S1 times e to the minus beta of S2. So basically just saying now that I can tell the two particles apart, so I can break up the sums into two separate sums. So here we were just treating it as like two systems with the same energy. We can't necessarily tell them apart. Now if you can tell them apart, you can just break them up nicely. And so again, since this one will only depend on the first particle, this one only depends on the second particle, then you can break these up further. This is all straightforward, like trivial math, but we gotta at least show it. I forgot an E here, didn't I? Yeah. So this just says that Z total is going to be equal to Z1 times Z2. That's for distinguishable. So again, if we have this two part system, but now they're indistinguishable, what do we need to do? What do we need to do to this Z total? Anybody? We can't tell them apart. So what kind of thing do you think we need to do to this answer right here? Because we overcount if we can't distinguish them, right? So what factor would we need to put on here if we're only talking about two systems? Yeah, divide by 2. So in that case, it'll just be 1 over 2, Z1, Z2. And this will extend readily if we have a system of n particles. So we do the exact same thing we did before. We just generalize all of this. So Z total for a system of n particles is going to be the product from I equals 1 to n. Maybe, hopefully you've all seen this symbol used for products before. It's like the same idea as the summation, but now it's a product. So it just says take Zi times Z1 times Z2 times all the way up to Zn. So this is what it'll be if they're distinguishable. And there's no factor we need to throw in there. What factor do we generalize 1 over 2 to if they are indistinguishable? Anybody? What do we remember from much earlier on when we were starting to learn about combinatorics? Yeah, 1 over n factorial. Very good. 1 over n factorial, Zi. So obviously we can just pull the 1 over n factorial out. Nothing depends on it there. And then Zi is just going to be Z to the n because they're all the same. So this will just be 1 over n factorial Z1 to the n, since all of the Zi's are the same. They're indistinguishable. Cool. So those were just some quick things we needed to show quick before we actually talk about the ideal gas again, because we're going to break up the ideal gas basically into its translational degrees of freedom and its internal degrees of freedom. And we're going to use this property right here. And just a bit of terminology that Schroeder wanted to make clear is that, I guess in his book, when he's using S, this refers to the system state. So the state of the system. And whenever he writes S with a little subscript like this, S1, S2, this will refer to a single particle state. So just know that when you're using his book that this is going to be the convention. Might change when you look at other books. But that's just life. All right, so now we get to end chapter 6 with our good old friend. We met on the first day, and we're going to see it all the way through. The ideal gas law. Okay, so let's suppose we have an ideal gas with n identical molecules. Well, then like we just said, the total partition function is just going to be this. It'll be 1 over n factorial to account for overcounting times partition function of a single molecule to the nth power. Easy. Okay, so now what we're going to do is we're going to take Boltzmann factors. Yeah, let's just do it here. So the Boltzmann factors look like this, E of S over KT. They always look like that. And in the case of an ideal gas law, we're going to break it up into translational types of energy and what we're going to call internal types of energy. So break up this E of S into, we're going to call this one E sub TR for translational. We're going to call this one E sub int for internal degrees of freedom. So that could be like vibrational or whatever other types of degree of freedoms you could think of. Vibrational, yeah, rotational. And we're going to break it up into 2 parts like this. Okay, so we know from what we were just discussing before that we can take each single particle partition function And we can break it up into the translational partition function and the internal rotation function. Partition function, rotation function. All right. So these two things are just defined as the following. So Z translational is just going to be the sum over the translational states with the Boltzmann factor here. Right here. ETR over KT. And likewise, the internal partition function is just the sum over whatever the internal states are. Just being very explicit about what we mean. Okay, so that's that. Now we're just going to basically focus on the translational partition function for the moment. So let's hop back into quantum mechanics. I know some people haven't taken it, but if you have, this will, well, you don't even necessarily need quantum mechanics for this. You've all taken like intro physics where you talk about waves, so this won't be that bad. So let's just consider a 1D box. Okay, so if we've got a 1D box, why am I drawing 2 dimensions if it's 1D? So if it's 1 dimension, so it starts there, ends there, and we want to put a wave function in here. What does the wave function have to do at the ends? Has to go to 0, right? That's what we mean by a box. So it's got to have a node there, and it's got to have a node there. So what's the maximum wavelength that we can fit in here in terms of the length L? So if we just want to fit like, yeah, we'll just write it. 2L, yeah, that's right. And if we want to keep on throwing more and more nodes in, we'll have a factor of 1 over n. So lambda sub n as a function of the number of nodes we squeeze into this box, it'll be 2L over n, where n is just 1, 2, 3, on and on and on. Just the allowed standing wavelengths. Okay? Now, I guess here's where the quantum part comes in. So if we take the de Broglie relation, which tells us how to calculate the momentum of a particle, or technically, I guess it's more so for calculating the wavelength of a particle, but we're going to use it for calculating the momentum right now. So if we know the wavelength, we can calculate the momentum by taking h over lambda, right? Hopefully you're familiar with that. So then we can use our expression for lambda here in this general expression. We can get a p sub n, the momentum, as a function of the number of nodes in this box right here. And we can get the following expression. It's equal to hn all over 2 times L. Okay, so far so good. Now, if we have a non-relativistic particle, how can we express its energy? Anybody? In terms of the momentum. So we know if we're talking about translational energy, it'll just be 1/2 mv squared. The expression in terms of momentum is just what? Yes, p squared over 2m, exactly. Cool. So we've got a momentum, we can plug it into our energy, and we can basically get the number, or the discrete energy states for this 1D box. So E sub n is equal to Pn squared all over 2 times m, which if we plug everything in, we've got Planck constant squared times n squared all over 8ml squared. So these are just the energy levels for a quantum 1D box, basically. All right. So let's take this 1D box model and think about for the moment that our ideal gas just lives in a 1D box. So, I mean, we always talk about our ideal gases enclosed in some volume V. So that's three-dimensional. Let's just think of it as being one-dimensional for the moment and apply this result. So if we take that, we can take what? So thinking of only the translational partition function right now. So z1d, I'll put that there just to be explicit. So that'll be the sum over n, right here, of e to the minus e sub n all over k times t. And if we take our expression that we just derived for the energy, we plug it in, we should get e h squared n squared all over 8ml squared k times t. That's all under a fraction. Okay. And so now we'll do the same thing that we were doing before in turning this sum into an integral. So we'll assume that we're at a high enough temperature, basically, that the temperature compared to these energy levels is enormous, so that the difference between these energy levels is so small that we can approximate this discrete sum as an integral. So unless we're talking about low temperatures or really small boxes, we can do this. So this is the translational, yeah, this is only the translational degree of freedom right now. We're only considering the translational partition function. That's right. So let's just assume that we're not talking about tiny boxes or really low temperatures. So in that case, we can take z1d translational, and we can write it as a sum, or an integral, sorry, from 0 to infinity of e to the h squared n squared all over 8ml squared kt. And you might notice something a little funny right here. So this n went from, 1 to infinity effectively. And now here I've just magically pushed it down to 0. In the grand scheme of things, that doesn't actually matter. Like that little from 0 to 1 doesn't matter at all. So you can totally forget about that. But do note that this sum goes from 1 to infinity. I'm taking 0 to infinity just because it's nicer. So this is just a Gaussian integral, like we talked about before. So we have a nice little formula for it. So if we put it in, we just get the following. We would get square root pi all over 2 times the square root of 8ml squared k times t all over h squared. Okay, I'm running out of space. Simplify this a little bit. 2 pi m kt all over h squared times L. So I'm just pulling the L out. And now I'm going to call this thing right here something specific. So I'm going to call this L over LQ. So I'm equating this expression right here to this expression. So this little L sub Q right here is 1 over this expression right here. And so, yeah, because this does have units of inverse length. So we can think of it as a so-called quantum length. Okay. So now, if we take that result and we go to 3 dimensions, so it's always easy to start in 1D and then just talk about 3D generalizations. So if we go to 3D now, then the translational kinetic energy is just px squared over 2 times m plus py squared all over 2 times m plus pz squared all over 2 times m. Okie dokie. So now what can we do? We can just use the same results that we found before. So we can write down the translational partition function as the sum over s e to the minus etr over k times t. But now etr is just 3 copies of the thing that we derived before. So you'll basically just get the sum over like nx, sum over ny for all of these different boxes and z, and you get the same expression that we had before, just 3 times. So I won't write it all over again because it's super, super annoying. But we'll get the same result. So each one will produce in Lx over what I called script L sub q, so the quantum length. So this will be Ly over little lq times Lz over little lq. Well, Lx times Ly times Lz is just what we call the volume. So it's just the quantum length cubed, which we'll call the quantum volume. Okay. So now let's go all the way back. Remember that our single particle partition function we had written as the translational partition function times the internal partition function. And now we have our translational partition function, so we can plug it in. We've got the volume all over, and I'll call this V sub q, all over little vq times z internal. Cool. So what can we do at this point? Well, now we've got it for a single particle. We can use our result for n identical particles to write the total partition function at long last as 1 over n factorial times the volume over the quantum volume and there we go. So we have, at this point, the partition function in terms of the translational partition function for the ideal gas of indistinguishable particles. So you might be wondering, well, what about this Z internal right here? Well, obviously that will depend on what types of internal degrees of freedom you're talking about. But generally this will be a lot easier to calculate than the translational one, right? Because we've actually we went through an example where we calculated the internal partition function for like a diatomic molecule. So you can go back and look at that and you just throw that in if you want to include that. But with this partition function now, you can calculate everything, right? So the only thing I'll do right now, and you can look at the rest in the book, but we can calculate, for example, the average energy. So we derived at the start of class this formula. So we said 1 over z del beta was the average energy, right? So we can also just write this as del over del z, or sorry, no, del beta log of z. The derivative of log of z is just going to be 1 over z and then the derivative on z with respect to beta. So if we take this derivative right here and we use this partition function right here, we can get the following. So let's see. U is going to be equal to minus n del over del beta ln of z internal. We won't explicitly evaluate that because we don't know what it is right at this point in time. Plus n times 1 over the quantum volume, derivative of the quantum volume with respect to beta. So this quantum volume does include factors of the temperature, remember? So the quantum length included this T right here. So this quantum volume just includes 3 factors of that. So it's going to have dependence on beta. Let's see. This expression right here is just the average internal energy. And if we take n times the average internal energy, well, that's just what we call U, the total internal energy. And if we evaluate this, we would get 3/2 nk times T. So let me just ask, is this piece right here what we should have expected? Should we have expected that the average energy that corresponds to only translational degrees of freedom should have produced an additive component of 3/2 nkt? Does this seem right? Anybody? So what does the equipartition theorem say? Right? It says that U is equal to N times F over 2 times K times T, right? So if we're considering only translational degrees of freedom, how many degrees of freedom does that contribute? 3, right? Yep, I'm seeing 3s. So that would be N times 3 halves N K, not an extra N, KT. Well, that's exactly what we just showed, but using the machinery of partition functions. So that's pretty cool, right? I mean, we have basically re-derived a result that we've been using a lot, again, in terms of partition functions. So at this point, like all the stuff we've done previously in class is hopefully making a lot more sense. Maybe less sense because this is potentially more complicated, but now you're finally understanding like the roots of where all of these expressions are coming from. So I think that's actually all I've got for chapter 6. And we will start chapter 7 next week. And yeah, and can we also get a U internal? Yeah, so U internal we talked about last class. I might even have like the slides. Let's see, let's go back a little bit. So we were evaluating, yes, we were evaluating the partition function for a diatomic molecule, remember? I don't know why this is so zoomed in all of a sudden. And so we went through all of this and we were able to calculate the contribution due to specifically a diatomic molecule. So if you wanted to calculate like the same kind of thing for other types of internal energy, you would just go through the exact same process, calculate the partition function, use this formula to calculate the internal average energy, and boom, you're done. So the only reason we left this undetermined is because it depends on what you're talking about. But in general, whenever we're talking about an ideal gas, it's always going to have kinetic energy. And so it's always going to have this term coming in some way or another. Yeah. It's a good question, though. Wow, I was really zoomed in that whole time, apparently. Are there any other questions about this? I know it was kind of another long-winded derivation, but there's obviously light at the end of the tunnel. I mean, you just get results that you've already been given, so that's always a good sign. Yeah, so hopefully this is giving you some more insight. If it doesn't, give it some time. Or talk to me during office hours or shoot me an email or something. We can chat about it. But yeah, so we're done with chapter 6 and we will be moving on to chapter 7 next week. And I would like to, in chapter 7, what I would like to get up to and through is blackbody radiation. Although it's maybe a little bit ambitious. We're not going to talk about the ending section, which I think is like the Debye theory of the solids. We're not going to discuss that, so you don't have to read it for class. But if you do want to read it, obviously go ahead and do. But just a little heads up on what our roadmap's going to be. So hopefully get up through blackbody radiation, and hopefully your homework will also cover that. But again, next week, I'll be helping you out with your homework more than usual so we can cover all this content in time without working you all to death. All right. So that's all I got. If nobody has any questions, I can let you go and have a great weekend. And I'll grade your exams and we'll chat more about how that went on Monday. Okay? Thank you very much. Have a great weekend, everybody. Bye.